Welcome to the webinar today. This is our EPA's monthly Small Drinking Water Systems webinar series. Today's topic is increasing analytical laboratory preparedness. And before we get started and I turn it over to Tom to introduce the presenters today, I'm just going to go over a couple things. You do have on your navigation bar located on the right side of your screen, there is a handout drop down. We did provide a copy of the presentations today. So they do have any live links that we're going to go over, and you're welcome to distribute those to anyone you think might benefit from them. To ask a question, so anytime during the presentation, feel free to type a question in the questions box. And again, you'll find that on your navigation bar. And we will have a Q&A session at the end of both presentations today, and we'll try to get to as many questions that you have as possible by 3:30 this afternoon. If you're having any issues also with hearing or you can't see the slides, just let us know in the questions box and we'll do our best to take care of that for you. Okay, and so also we are offering one training credit hour for this webinar. In order to receive that, you do have to attend the live webinar. And I say that because we do post these recordings on our webinar website, but you can only receive a certificate for attending live. And you do need to attend for at least 60 minutes to receive that. If you have people in the room with you who are not logged in and they'd like a certificate, on step 3 here, you can see the email address. It's best to send it to that email address and we'll make sure they get their certificates as well. Just kind of a shout out for our annual workshop coming up. I'm sure a lot of you have heard about this, but we hold an annual drinking water workshop every year in Cincinnati, Ohio. Registration is still open. The workshop is September 24th through 26th. Does provide great networking opportunities and a lot of current information for drinking water systems. Now, if you know people who can't attend, or if you can't attend but you'd still like to get some of the information, we are offering live broadcasts. If you click on the link here when you get a chance, you'll see the information on how to register for those, and we are offering 4 live broadcasts from the workshop. And you are actually eligible for training credits for those as well. And here, these are some upcoming webinars here, and the links are here on this slide. So if you get the handouts, you can easily find these. These are all coming up in September, and you'll see at the bottom the live broadcasts that I mentioned from the workshop. These are the 4 technical sessions that we'll be offering live from the workshop. And with that, actually, one more thing before I turn it over to Tom. In case you didn't take the poll, if you do have more than one person in the room with you, if you could type that number in the questions box, we'd really appreciate that. It helps a lot with our outreach efforts. And with that, I'll turn it over to Tom.
Great, thanks, Michelle. Can you hear me?
Yep.
Great, thanks, Michelle, and thanks everybody for chiming in. Our first speaker is Heather, and Heather's an environmental scientist with Region 3 in the EPA, and she is the lead. She is the public notifications rule lead, assisting with the direct implementation of the Safe Drinking Water Act in the District of Columbia, and supports the water team in preparing for emergency responses. Before she came to Region 3, she was with the Office of Groundwater and Drinking Water for 5 years, and she has degrees from the University of Delaware and Drexel University. And with that, I'll hand it off to Heather.
All right, thanks, Tom, and I am up and running here. So good afternoon, everyone. Today, I would like to talk to you about a video that EPA Region 3 developed recently. And in this video, we focus on calibration verification for chlorine residual measurements. So today I'm going to give you sort of an overview of what's in the video, and I'll also provide you the links so that you can go to the video and actually watch it on YouTube and get a little bit more in-depth information as opposed to what I'm giving you today. So the calibration verification procedures that I'll talk about apply to both portable and benchtop instruments for field grab samples of chlorine. Today I'll also go over the differences in using primary standards for calibration checks versus using secondary standards, and then I'll tell you where you can go to learn more in both the video and then a few other references that might be handy if you're doing this. So why is this important? Why was I asked to share this information with you today? Well, a few years ago, EPA's Philadelphia Regional Office of Drinking Water was involved in a research project, and we learned that most of the drinking water systems participating weren't following the required quality assurance procedures that are in EPA's Method 334. Our researchers followed up on some of these findings, and we found that many of the small public water system operators don't check their instruments using a prepared chlorine standard, and this is required by Method 334. They also weren't performing the initial demonstration of capability, and they also weren't performing the routine quarterly calibration checks. So for those of you who might not be familiar with Method 334, it's an EPA method that was released in 2009, and it allows the use of any type of online chlorine analyzer for compliance monitoring when it's used in conjunction with a grab sample reference method that's approved for drinking water compliance monitoring. So in other words, it's a quality control protocol for chlorine analyzers used to collect regulatory data. And the method's intended to be used when chlorine residuals, either free or total, are in the range of 0.2 milligrams per liter to 4 milligrams per liter. It's applicable to entry point and distribution system monitoring, and using Method 334 doesn't necessarily ensure that you'll be in regulatory. Oh, hello? Yes?
No.
Oh, I hear an echo. Can everyone hear me okay? Are we? Okay. Sorry about that. Method 334 doesn't necessarily ensure that you'll be in regulatory compliance, but if you follow it, it will help verify that your compliance monitoring is valid. So then kind of the bigger picture, why does that matter? Why do we care that we have accurate chlorine measurements? Well, really, accurate measurements of chlorine is critical to protect the health and safety of the public through proper drinking water chlorination, and also to ensure that there's correct compliance reporting under the Safe Drinking Water Act. Chlorine measurements are required for the Safe Drinking Water Act's maximum residual disinfection levels, chlorine residual limit. They are also required for the the revised total coliform rule, groundwater rule, disinfection byproduct rule, surface water treatment rule, other compliance monitoring, and they also might be important during system repair or maintenance, say flushing. If you're putting in new storage tanks, you'll want to make sure that you have accurate measurements of your chlorine. Accurate measurements also have an economic impact, since the analyzers are required to control the dosing and therefore the consumption of chlorine or chlorine-based chemicals. And then finally, it's important because chlorine residual testing is the one chemical analysis that operators and samplers in all public water systems have to perform. So what are some of the major obstacles with calibration verification? Why did EPA find that a lot of systems weren't doing this or weren't doing it properly? First of all, small public water system staff don't typically have extensive laboratory experience, and operators are often unfamiliar with preparing chemical solutions or the calibration check statistics. Also, state operator certification requirements don't always include the demonstrated capability for instrument calibration, and in addition, state requirements might vary. Method 334 quality assurance procedures might not be emphasized at the state level. I know doing research for this video, we did find some states that are really emphasizing it, but it does vary throughout the country. So before I talk to you about actually doing the calibration verification, I'd like to go over a few definitions. So first, it's important to talk about the difference between primary and secondary standards. Primary standards are aqueous standards, and they span the concentration range that's expected in your grab sample. Primary standards come in a NIST certified concentration, NIST being the National Institute of Standards and Technology. They have to be diluted following the chlorine dilution standard procedure, which I will cover in some of the upcoming slides. And primary standards can also can be used to calibrate an instrument and also check the calibration of the instrument. Secondary standards, on the other hand, can be purchased to use with most DPD spectrophotometers or colorimeters. The accuracy of these secondary standards has to be verified on each recently calibrated meter for which they're going to be used. And this is really important to keep in mind that secondary standards may not be used to calibrate the instrument. Only primary standards can. I should also point out that at this time, only a few chlorine kit manufacturers provide secondary standards. I know Hach and Lamont do. There might be others out there that I'm not aware of. We just haven't used them personally here. And typically, the secondary standard sets contain 4 vials. They contain a blank and 3 standards that are filled with either a gel or a liquid that simulates the chlorine at various concentrations. Each set of standards is specific to the manufacturer and to the meter's analytical range. A lot of times you'll get the 3 standards, you'll get a low range, a mid-range, and a high range. Some manufacturers just do a low range and a high range. The chlorine dilution standard. These are primary chlorine standards that are then diluted to an appropriate concentration. These are used for routine quarterly checks, the initial demonstration of capability, and the initial instrument verification. And to calculate the concentration that you'll need, you need to use the formula that's on the screen here. C1V1 equals C2V2. And here, C1 is the concentration of your primary standard. V1 is the volume of the primary standard. C2 is the concentration of the diluted standard. And V2 is the volume of the diluted standard. And this formula is based on the premise that when you do a dilution, the amount of material in the solution remains the same. So a little bit further in my presentation, we'll walk through this formula in greater detail. If you really want to break down the math of it, go watch our video, and we really get into it there. So a method blank. Method blanks used to account for interferences or contamination that results from the analytical process. It's an analyte-free matrix or reagent-grade water to which all reagents are added in the same volumes or proportions as used in the standard measurements. The method blank is carried through the complete sample preparation and the analytical procedure. The initial calibration is a procedure that uses diluted calibration standards to ensure the accuracy of the instrument. So as it kind of sounds, when an instrument's new, or even if it's just been repaired and sent back to you, samplers have to verify the internal factory programmed calibration curve for the grad sample instruments before placing them into service. So to verify this calibration curve, the samplers have to perform a method blank and at least 3 calibration standard dilutions that match the instrument factory calibration dilution. The initial demonstration of capability, also known as the IDC, is a procedure that's used to assess the ability of the analyst to generate acceptable precision and accuracy. And this has to be successfully performed prior to analyzing any field samples. So if you are a sampler taking chlorine residual measurements and you've never performed an IDC for your instrument, you should go do it. You need to perform the procedure once for each instrument that you use. And if you have different people using chlorine instruments, each person should perform an IDC for each type of instrument that they use. And this initial demonstration of capability consists of doing a method blank and also 5 replicate dilution standards at the same concentration using either the mid-range of the instrument or close to your expected reading. And the precision and accuracy of the 5 replicate samples should be within 15%. If not, you have to repeat the process until you can get to that 15% or better. So I won't cover the full IDC process today, but as I mentioned, go to the video, you can watch it, and all the steps and calculations are explained there. EPA, and I know the Pennsylvania DEP, we also have worksheets that are posted on the web that'll help you do some of the calculations to make sure you're within the acceptable range. Most of the time, you're going to be doing quarterly checks. These quarterly calibration verification checks require the preparation and analysis of diluted primary standards once every 3 months or quarterly. They ensure that the instruments, the glassware, and the reagents are still providing you with accurate results. And these checks start with a method blank measurement and then a calibration verification check using one chlorine dilution standard with a concentration near the mid-range or the expected concentration that's in the field. A secondary check standard verification uses secondary standards to verify the accuracy of the instrument. This can also be a surrogate to verify instrument performance between primary standard verifications, and these checks should be performed daily or anytime an instrument hasn't been used for a significant amount of time. So for example, you should perform the secondary check in the morning after the instrument's been off all night and you're planning to use it that day. So I mentioned this earlier, but just as a reminder because it's important, secondary standards cannot be used to calculate. The secondary standards must also be verified on the specific meter for which they'll be used if it's been recently calibrated. Meters have to be verified for all tested chlorine ranges. So for example, if a chlorine concentration is observed greater than the limits of the low range setting, then you have to use a meter with a mid-range or a high-range setting and verify that using the appropriate secondary standards. And generally, secondary standards must be measured within 10% of their expected concentration. Performance evaluation, also known as a PE, is a test of unknown certified standards measured by an analyst to demonstrate the proficiency of the analyst. So if your primacy agency requests it, or if your water system decides to perform a PE, then you have to purchase a certified standard solution of chlorine that has an unknown concentration. And the PE procedure describes the amount of the certified standard that you need to add to a known volume of purified water. And then the measurement of the unknown concentration can be checked for individual analysts by reporting the results to the certified solution provider for comparison to the allowable range. And this is really good practice. It's not something that's necessarily required by EPA. So let's do this. In the next few slides, I'm going to try and walk you through a summary of some of the steps. It's a little bit difficult, at least for me, to think about this all in my mind and picture it as I explain it. So again, I highly encourage you to watch the video to see how everything's done. There you can slow it down, you can rewind it, pause it, really take your time watching it and learning the steps. But I will do my best to summarize it here. So first, before you perform any measurements, you'll want to perform a method blank. And as I said before, a method blank is a measurement that uses reagent grade water, and you follow the same analytical steps as you would for the standard measurements. The purpose is to determine whether there is any interference from our sample vial or reagents, so that we can account for that interference when we measure our standard concentrations. So first, you fill a sample with purified water, and you have to ensure that the vial isn't scratched or stained. You'll rinse it a few times with reagent water, and then you'll wipe the vial to remove any fingerprints. You put the vial in the instrument and align the vial according to the manufacturer's recommendations. So at least on the instrument that I've used, there are two little arrows that you want to make sure line up and face each other. Then you'll place a cap over the sample vial and push the 0 button, and the display should read 0.0. Then you'll take the reagent and add it. You want to mix the reagent by placing the cap on the vial and slowly inverting it to mix. You then place the vial back in the colorimeter and take another reading, and the reading should be less than the minimum chlorine residual required by the state, or 1/3 the lowest standard used for the calibration curve that's provided by the manufacturer. Next, you'll want to know how to prepare standards that are used for the equipment calibration verification, since, as I mentioned, primary standards don't come in the exact concentrations that you'll need. And also recall that chlorine dilution standards are necessary for multiple QA processes, including the routine quarterly checks, the initial demonstration of capability, and the initial instrument verification. So you first want to gather all of your equipment that you'll need for dilution. And this includes a NIST concentrated primary standard, plus something you can empty them into. You need an adjustable pipette and tips to measure the volume of the primary standard, a Class A volumetric flask, and 100 mils is generally a good size for this. You'll need the reagent grade water and a bottle to dispense it, and then gloves, safety glasses, and a calculator. And this is probably one of the most challenging parts of the chlorine calibration procedure. It can be difficult to pipette the chlorine standards properly, and it definitely is something that takes practice. So first you'll fill the flask approximately 3/4 of the way with purified water. And then remember that equation we talked about earlier with the C1V1 and C2V2? I'm going to go into a few details on it here, but as I said, if you really want to get into it or remember how to do some of the calculations, just check out our video and it'll walk you through in a slower pace. But here I've edited the formula into one that makes a little bit more sense to me. So it's C1 V flask equals C standard V add, and you can see the original C1 V1 below it. But here we know C1, V flask, and C standard, and we want to find out what V add is, the volume of the primary standard that we need to add. So since chlorine is only coming from our standard solution, we know the amount of chlorine is the concentration of our primary standard times the volume of the standard we're adding. And this must be equal to our diluted concentration of chlorine in the 100 milliliter flask times the concentration of the chlorine in the flask. So we know C1, V flask, and C standard, and we want to find V add, which is the volume of the primary standard that we need to add. So once you do that calculation, you'll pipette that amount of primary standard into the flask, and then you fill the flask the rest of the way with purified water. And you want to try and have the bottom of the meniscus right at the fill line. Then you're going to cap the flask and invert it several times to mix, and the prepared diluted standard is now ready to go. And you should also note that the prepared standard should be analyzed as soon as possible after the dilution, because the chlorine in the solution can off-gas pretty rapidly, which will change the concentration of the standard. Now to perform the measurement, to take the chlorine dilution standard measurement, you want to first turn on the colorimeter and zero the instrument. Then you'll rinse your vial with reagent grade water and a small amount of the standard and wipe it clean. Then you'll remove the vial, add the DPD reagent, and the DPD reagents can be used for free chlorine or total chlorine. You'll want to select either free or total on the meter based on whatever type of disinfectant residual you have. You'll mix the reagent by gently inverting the vial with the cap on. You don't want to shake it up too vigorously or you'll cause air bubbles. And then if you're measuring total chlorine, you need to wait 3 minutes for the color to develop. But for free chlorine, you can take the reading right away. So you'll take the reading, and this is what is known as the concentration measured, and it will need to be adjusted by the concentration of the method blank that was performed. And then you rinse the vial, and you're good to go. And as I said, go back to the video, watch it, and you can see somebody actually do all of these steps. So here is a table that sort of summarizes the procedures and standards that are required for performing the calibration verification checks for a chlorine meter. It also gives the method 334 reference section, so you can go there and find more detailed information on each step. And then just keep in mind that validating the factory calibration curve and performing the initial demonstration of capability are just one-time startup procedures. The routine calibration check must be completed at least quarterly. And then keep in mind that every sampler or analyst has to demonstrate their ability to perform the analysis consistently, ensure the instruments are working properly, and then make sure that the reagents they're using are effective and not expired. You also want to properly document the steps you're taking consistent with your state or local regulations. A lot of times the documentation might include the dates that it's performed, measurement of the standards, the instrument used, the standard product number, and the expiration date. But as I said, check with your state and local regs to make sure that you're documenting everything properly. Here I've highlighted some common issues and problems that you might come across during the chlorine calibration verification process. You want to be very careful about keeping the equipment and glassware clean. You also want to make sure that you have the proper equipment and align the sample cells per the manufacturer's recommendations. Don't ever use expired standards. Remember to check the batteries, those die from time to time, and always follow the user manual and method instructions. And just keep in mind that we're doing all of this to ensure that we get accurate measurements of field grab samples. It's important to take your time, don't rush the process. There's no point in taking the samples if you're not going to take them properly. And as I promised, here is a link to our video. So in the handouts, you should be able to click on that and it'll take you right to it. You could probably also do a Google search and find it, but go ahead and check that out when you get the chance. The video does show you the equipment and supplies that you need to do all of the steps I talked about, how to prepare the standard chlorine solutions and actually calculate the dilutions, and then how to perform the calibration verification. Here are links to EPA's Method 334, and I also put in links to Pennsylvania's information on Method 334. Pennsylvania has some great videos that go into even more detail than EPA's do, and they also have some really cool job aids and an IDC calculation spreadsheet that are posted online. So if you want to get even more into it, please check that out. And I apologize, there might be some other great state references out there as well. There most likely are. I'm just more familiar with Pennsylvania since that's where I live and work. And with that, I just want to say thank you. Go check out the videos, and I will answer some questions at the end. Thanks.
Okay, great. Thank you very much, Heather. As Heather said, we'll be answering questions, and we'll be answering questions for both speakers at the end of the second talk, so hang on for that. Also, if you have questions that from Heather's talk or even in the middle of George's talk, the second talk, please go to the question section on your pull down and type in your question ahead of time. That helps us organize the questions so that we can hit the ground running when it comes time for questions. So we generally handle questions a little bit before the hour and then going all the way to about 3:30. So another housekeeping issue is that if you have, just a reminder that from what Michelle said, if you have more than one person in the room, if you could go to that question box and just type in how many people are in your room, if it's more than one. If you have only one yourself, don't bother. And so if you have more than one, put it in. It helps us document how many people are calling in or listening in, and that helps us justify these webinars. And that's about it. So I'll introduce George, our second speaker. He's a physical and analytical chemist with the Water and Laboratory Alliance team in EPA's Water Security Division. He works with the Analytical Preparedness Full-Scale Exercise Program and the Water Contamination Information Tool. And George has degrees from Yale and the University of Virginia. And with that, I'll hand off the podium to George.
Great, thank you very much. And thank you for giving me the opportunity to speak to you today about the Water Laboratory Alliance team and how we can help you all prepare for and respond to water contamination incidents. So to go over the structure of the talk, I'm going to begin with an introduction of who we are and a brief history of the drivers that created the Water Laboratory Alliance, as well as how it fits in with other federal lab network support efforts. Then I'll go on with an overview of the organization of the WLA and some of the benefits of membership, including the way the Lab Alliance is organized and the benefits that it can provide to drinking water utilities. Then I'm going to transition into discussing some of the available tools, resources, and training that we've developed over the years, including some of our existing tools and resources that may be beneficial to your organization, including the Lab Compendium, the Water Contaminant Information Tool, and our COOP template for laboratories. We also have other resources that are recently developed that I'll be able to go through in a little bit more detail. So with that, I'm going to talk about who we are. As you can see, we're a part of the overall EPA Environmental Response Laboratory Network. The WLA team is the part of the network that focuses solely on water, although EPA has the environmental laboratory capability to analyze all environmental matrices. But the WLA provides the water sector with the laboratory capabilities and capacity to analyze water samples in the event of natural, intentional, or unintentional water contamination incidents involving chemical, biological, or radiological contaminants. The Environmental Response Laboratory Network, or ERLN, is EPA's response to Homeland Security Presidential Directive 9, which encompasses an all-hazards approach that provides laboratory capabilities to analyze air, soil, surfaces, and water for chemical, biological, or radiochemical contaminants. The WLA is part of the ERLN, as I mentioned, and it provides the water sector with a nationwide network of laboratories to support the response to water contamination incidents. The network is composed of water, public health, environmental, and commercial laboratories that have the capability and capacity to analyze water samples in the event of natural, intentional, or unintentional water contamination. Combined, the ERLN and WLA serve as a member of the larger Integrated Consortium of the Laboratory Networks, or the ICLN. The Department of Homeland Security is the chair of the ICLN. And the ICLN provides the mechanism by which laboratory networks can share information, optimize and coordinate resources, and conduct strategic planning across the federal government. The ICLN has continued to expand over the years and incorporates additional laboratory networks led by our partner agencies to address analytical needs from a variety of utility sectors. So what does it take to be a member of ERLN and WLA? It's free to participate in ERLN and WLA, and it's open to all laboratories that meet the requirements for membership. And these include, first, that a laboratory must have a current quality management system, which can be the National Environmental Laboratory Accreditation Program, the International Organization for Standardization, or ISO 17025, drinking water certification, or be able to make an appropriate demonstration of an equivalent quality management system. To become a member, your laboratory must have analytical capabilities and capacities for chemical, biological, and/or radiochemical contaminants in environmental matrices. Your laboratory must agree to use ERLN methods and reporting requirements as requested, and will need to ensure data and information security. Laboratories must participate in proficiency testing programs and may be subjected to audits as appropriate. In most cases, the ERLN program office will request results of previous audits to minimize disruption of laboratory operations. When required, laboratory evaluations are carried out to monitor the laboratory's ability to provide analytical services. Specialty laboratories, such as radiochemical laboratories, must meet laboratory-specific health and safety requirements. And finally, all member laboratories need to maintain a profile in the laboratory compendium, which I'll discuss a little bit later in this talk. At the moment, WLA membership is available to two organizational categories: laboratories and water utilities. Although, even if you don't meet the requirements that I laid out before, other categories might be added in the future. We discussed the possibility of some sort of associate member category, if it may be possible. But I went through all of that, even though it may not be applicable to all of the attendees on this webinar, so that you understand that when you access the WLA, this is the type of rigor that we apply to membership. So there are several benefits to membership in the WLA, and those include increased visibility and enhanced credibility by being part of a federal laboratory network, improved emergency preparedness and enhanced networking through training and exercises, opportunity to analyze samples based on your laboratory's capabilities, access to analytical expertise and potential in-kind support, access to newly optimized EPA methods. There are opportunities to receive compensation as determined by the parties who are requesting services. As a utility, you know that if you contract with a laboratory that is a member of the WLA, they will have access to the WLA tools and benefits that will make it easier for them to serve you in an emergency. In addition to members, the WLA community includes liaisons, who are individuals in other types of organizations, such as state and local departments of environment and health, as well as first responders, who champion the WLA, such as by disseminating information and identifying water sector and emergency response sector needs. So our membership fluctuates a little bit, but it's been holding steady for several years at around 140 members across the country. We are accepting new applications for membership from everywhere in the U.S., but we'd be especially excited if we had coverage from all 50 states. Now, discussing the Water Laboratory Alliance Response Plan, which is a little bit, which is basically the core of the program. To enhance incident response, the WLA created and finalized the WLA-RP, which is the result of best practices and lessons learned that we collected through regional exercises and provided by stakeholders. The WLA-RP provides a comprehensive national approach to coordinated laboratory response to water contamination incidents. Specifically, the WLA-RP addresses incidents that may require additional laboratory support and a broader response than a typical utility, state, or federal laboratory can provide. The WLA-RP includes best practices that can be used to coordinate laboratory responses for any situation, from a multi-regional incident requiring support from many laboratories to a local incident that only requires a single laboratory. The WLA-RP provides laboratories with a structure that can be used in conjunction with existing incident command system structures and procedures, and provides guidance on issues such as communication, sample analyses, and data reporting. The link for the WLA-RP is provided on the slide. You can also access the document through the WLA homepage, which we'll provide at the end of the presentation. In recent years, there have been several water incidents that required analytical support, going back as far as 2010. As a result from a water main break in Boston, Massachusetts, the New England Regional Laboratory requested in-kind support of laboratory supplies for analysis. And after the Fukushima incident, a WLA and ERLN laboratory was asked to analyze drinking water samples for cesium-134 and 137. In 2014, in Eden, North Carolina, there was a coal ash spill that required laboratory support to conduct particle size distribution analysis of water samples. And finally, while no ERLN or WLA laboratories were involved in the Toledo, Ohio microcystin contamination incident, the incident did serve to demonstrate the need for effective communication and coordination during incident response. So with that background, I'm going to go into some of the tools and resources that our program makes available to the water sector, including to small water systems. So just as a conceptual exercise, have you or has your organization been involved in the response to a water contamination incident? If you have, it's probably useful to think of a few questions, such as what went well? What could have been improved with your response? And did you have access to the resources that you needed to address the issue? And that's sort of where we come in. No incident response will be perfect, but you can always improve your preparedness. So we've developed a number of tools and resources to aid in the laboratory response to drinking water and wastewater contamination incidents. These include the Analytical Preparedness Full-Scale Exercise Toolkit, Sampling Guidance for Unknown Contaminants in Drinking Water, the Water Contaminant Information Tool, or WISIT, a Continuity of Operations Plan template for laboratories, an Analytical Preparedness Self-Assessment tool, and live and on-demand training. The Sampling Guidance for Unknown Contaminants in Drinking Water is a guidance document developed by WLA that integrates sample collection, preservation, and transport procedures to support multiple analytical approaches for the detection and identification of potential contaminants in drinking water. It provides utilities and laboratories with an example of what would be required for a comprehensive sampling program and can be used to enhance laboratory, utility, and emergency responder preparedness by supplementing emergency response plans that you may already have. The screenshot on the slide here is from Table 7-2 in the document that provides useful information that is helpful when collecting and transporting samples, in this case for chemical and toxin analytes. The sampling guidance is available on the EPA WLA website and was recently updated. The next tool I'm going to talk about is the Water Contaminant Information Tool, which is EPA's secure web-based database of information on priority contaminants of concern for all hazards in drinking water and wastewater systems. It was originally developed in response to the 9/11 attacks, so that's where the initial suite of contaminants came from. However, it was re-released in 2005 after Hurricanes Katrina and Rita and other unintentional contamination incidents took place. And so it has evolved into an all hazards response tool. And it describes contaminants that would pose a serious threat if accidentally or intentionally introduced into water systems. And it currently contains over 800 contaminants of highest concern. The data in the database are peer-reviewed and regularly updated and are specific to the needs of drinking water and wastewater systems. And it is being updated for consistency with ORD's, our Office of Research and Development's, selected analytical methods for environmental remediation and recovery. So the URL is provided on the slide. Now that's an overview of WSIT. As you can see, here's our search bar. Let me show you a few screenshots of the types of useful information that you may find yourself needing during a contamination incident. The search feature is one of WSIT's most powerful and fundamental capabilities. You would type in a contaminant name if you would like to search for the name by selecting that radio button, and then it would direct you to a search button. And then once you click your contaminant, here in this case, methanol, it'll provide you a link to the contaminant profile. There's a left-hand menu that provides the types of information that are populated in the profile, although the first two, a general information and summary, are highlighted by default. You can check all, or in this case, if you're interested in fate and transport, you can check that box and that will bring up that information. We also provide available field and laboratory methods, as you can see. We provide method number, description of the methods, the media that it's designed for, a link, and whether it's screening or confirmatory, as well as the required instrumentation. For field tests, we describe the system itself and a link to the test kit for more information. So that's the Water Contaminant Information Tool. Next, we'll discuss the Laboratory Compendium, formerly known as EPA's Compendium of Environmental Testing Laboratories, which is a secure online database of laboratory capability to analyze environmental samples for chemical, biological, and radiochemical contaminants. Once you look up the methods that are going to be useful for identifying a specific contaminant in WSIT, for example, you may want to know who can actually analyze for it, and that's where the laboratory compendium comes in. The database can be searched by federal and state agencies as well as water utilities to locate laboratories that can provide analytical support to environmental contamination incidents. Here's a screenshot of our search page. As you can see, you can search by the name, the lab type, which EPA region you're interested in, the location by state, whether it's an ERLN or WLA member or a mobile lab, what type of analytical capabilities you're interested in. In this case, organophosphorus pesticides are highlighted. What type of support services are needed, and what special sample handling requirements you may have. And with that, you can search and get a list of laboratories. So both WSIT and the lab compendium require registration in advance, so it's a good idea to apply for access to those systems before you need them. Another tool or resource that we've developed in recent years is accessing laboratory support. This is in response to one of our most frequently received stakeholder questions, which is, how do we identify the laboratory support we need to respond to a water contamination incident? This is a self-paced training that includes scenarios when you might need analytical support and guides viewers through 5 potential routes to access it. It builds from the local to the state to the federal levels. The next tool we have is the WLA Analytical Preparedness Self-Assessment, which is an easy-to-use starting place for the water sector stakeholders to assess and improve analytical preparedness for water contamination incidents. Upon completing the tool, the APS will generate a series of recommendations based on your responses to enhance your organization's preparedness. Stakeholders that will particularly benefit from this assessment are drinking water and wastewater utilities, state, federal, and commercial laboratories, emergency managers, first responders, hospitals and other public health officials, local and state governments or primacy agencies, and EPA on-scene coordinator groups. The format of this is actually an online, basically quiz. So for each of the 21 questions, you would select the response that most matches your organization's capability, and then at the end it will populate a list of resources that you can use to help improve your preparedness. Your responses are not saved anywhere, so it's mainly just for your own use. After that, I'm going to discuss the Analytical Preparedness Full-Scale Exercise Program run by the WLA team. Our full-scale exercises have enabled participants to practice a coordinated laboratory response to major environmental and public health incidents using the WLA-RP best practices as a basis for response efforts. These full-scale exercises provide a number of benefits to participants. Utilities have the opportunity to identify and coordinate laboratory support, and laboratories gain familiarity with the WLA-RP, practice their own internal response procedures, and develop capability and capacity through the use of newly optimized methods. The full-scale exercises also provide the opportunity to build relationships between exercise participants that help facilitate communication and increase understanding of roles and responsibilities of utilities, laboratories, and other response partners during an emergency response effort. They'll also help exercise participants identify improvements to their internal standard operating procedures, and they allow the practice of analytical and data reporting capabilities to help build laboratory capability and capacity. Laboratories gain proficiency with newly optimized methods, and in some cases, the data that are collected during these exercises can be used to support method validation efforts. We've received a lot of positive feedback from participants during our pilot exercises. So based on that feedback, originally these exercises were run coordinated through the EPA regions. However, we decided to scale up the program and allow utilities and laboratories to plan and conduct their own exercises. So we developed the Analytical Preparedness Full-Scale Exercise Toolkit to meet the demand for such exercises. And the APFSC toolkit increases opportunities for organizations to participate in an exercise by allowing any interested stakeholder to take the charge of planning and conducting these exercises. The toolkit is an interactive PDF that includes example scenarios and associated exercise documentation that can be used as is or customized to meet your own needs. It's available for free on the EPA website. Utilities, state labs, EPA regional labs, and other state and federal agencies may use the toolkit to plan and conduct exercises. While EPA will no longer lead the planning, we will continue to play an advisory role to ensure success of your exercise. As with past APFSEs, the toolkit is designed to be consistent with the Homeland Security Exercise and Evaluation Program, or HSEEP. The toolkit includes both examples and templates that can be used by exercise planners to develop the required documentation for the exercise. These examples are fully completed documents that can be used as is or modified by the planners to achieve their goals. Each example is presented on a page similar to this. This page shows two scenarios that are included in step 4 of the toolkit. These documents can be downloaded, modified if desired, and distributed as needed. The toolkit currently includes 2 example scenarios, one of which is the contamination of a drinking water with the organophosphate pesticide dicrotophos. The second scenario involves contamination of drinking water with E. coli 015787 after heavy rainfalls cause runoff from agricultural areas. Both of these scenarios can be downloaded from the toolkit. I should note that one of our pilot utilities actually adapted the E. coli 015787 exercise for a wastewater utility-led scenario. We're currently in 2019 piloting a new scenario that will be added to the toolkit based on a Yersinia pestis scenario in drinking water. Considerations for scenario development are provided in the toolkit, including evaluating likely threats and contaminants. You may wish to consult the Water Contaminant Information Tool to obtain detailed information about a variety of potential contaminants. So with that, I'm going to transition to the WLA Training Center, which is an online resource developed to familiarize stakeholders with WLA response procedures, best practices, and supporting tools. The WLA Training Center ensures that members and stakeholders can take advantage of the WLA benefits and cooperate effectively in the response to water contamination incidents of all types. The current course offerings are provided on this screen, and you can see when the next ones will be offered on our website. Most importantly, all of the courses are provided free of charge. And there are 2 training courses related to the WLA-RP, the WLA-RP training module and the live tabletop exercise webcasts. As utilities who may be handling samples and sending them out to laboratories, you may be interested in the chain of custody training, and for your own information, the ultrafiltration videos that we provide on our website as well. So one of our closing thoughts is that it's important to remember that a disaster is not the time you want to be exchanging business cards. You want to make sure that you have those connections in place so that you know who to call when a disaster occurs. Having a robust knowledge base, tools and resources that improve resilience and response, and a network of professionals to call upon before and during emergencies will help your utility build preparedness. The tools and resources provided by the WLA can help you improve your readiness for emergencies. Membership in the WLA can also ensure that you're connected to a community of utilities, laboratories, and other technical assistance providers who are on the forefront of preparedness. So you're strongly encouraged to establish relationships with your response partners prior to a water contamination incident. So going through this list, do you know who you would call from each of these types of agencies you may need to reach out to? If not, then that may be something that you can think about and practice when you use the tools that we provide. So with that, I want to thank you very much for your attention. My contact information is up on the slide, as well as that of my team lead, Letitia Mapp. Please reach out to us at any time or to the team by contacting us at wla@epa.gov. With that, I'll turn it back over to the organizers.
Thank you very much, George and Heather, for your great talks.